We use mathematical modeling a lot in not only in geometry but other areas of mathematics, or even in the real world in terms of application problems. We'll model something or simulate something and see if we can figure out, is there a pattern or a rule that's being used over and over again. So in this problem here, we're going to basically come up with a rule over 2 steps. So problem number 1 asks you to draw all the diagonals from vertex A. The biggest problem that students have is they want to draw all the diagonals, and in doing so, they miss what's actually happening, what actually is happening mathematically. So please draw only the diagonals from vertex A, and then below that there's a table. So go ahead and complete number 1 as well as fill in the information for the table. Turn the video back on when you're finished. So a diagonal by definition is a line segment that connects 2 vertices that are not already connected as sides. So a triangle has no diagonals because the 3 vertices are already connected as sides. For quadrilateral, there is 1 diagonal that can be drawn from vertex A. For a pentagon, there are 2. For a hexagon, there are 3. And for a heptagon, there are 4. So again, you're only drawing in the diagonals from a single vertex, not all the diagonals. So the answers were 0, 1, 2, 3, and 4. So using your table, I'd like you to predict the number of diagonals that can be drawn from point A in a 10-gon, called decagon, and a 12-gon, which is also called a dodecagon. So look at the number of sides, look at the number of diagonals. Can you predict a pattern? So in other words, if I put the letter N here, can you come up with an expression using N that would allow me to predict the number of diagonals drawn from a single vertex for any polygon? So go ahead and write down what you think the answers are going to be, and then check your answers by drawing all the diagonals for vertex A, for a decagon and dodecagon. Turn the video back on when you're ready to continue. So for a decagon, hopefully you found there were 7 diagonals. And for a dodecagon, hopefully you found that there were 9 diagonals. So what's the patterns that's being duplicated over and over again? So one of the questions I posed was, if n represented the number of sides, then what n expression could I use to determine the number of diagonals? So hopefully you noticed that the number of diagonals is always 3 less than the number of sides, or another way, or number of vertices, because the number of vertices and the number of sides is actually the same number. And the reason why there's a difference of 3 is because if I would draw a polygon, say a pentagon, for example, and if I connected the sides to make the pentagon, I'm going to draw a point or a diagonal from this is my A, from here to here, so I'm using that point, and I'll draw a diagonal from A to this point here. But every time I do that, 3 vertices are never used, because those 3 vertices are already connected to A as sides. And so the number of diagonals you're actually drawing to the vertices is always going to be, the number of vertices is always going to be 3 less than the number of sides, because 3 of the points are never going to be used. All right, so here they're asking you to return back to page 1, and then draw in all the diagonals and then record the number. So keep in mind that the number of sides we already have, the number of diagonals, that rule is n minus 3. And we came up with 0, 1, 2, 3, and 4. And what they want you to do now is go back and draw in all the diagonals and then record your answers in the next row. When you're finished, turn the video back on. So I've drawn in all the diagonals myself, and so hopefully you found the triangle is still 0. because all the points are already connected to sides. Total of 2 for the quadrilateral, 5 diagonals for the pentagon, 9 for the hexagon, and 14 for the heptagon. So what I'd like you to do is take a look at the table and see if you can come up with a formula. So the numbers, using the number of sides and using the number of diagonals. Is there any way to use these two numbers to get the total number of diagonals? So you think about how I can use these two numbers here to get to the final answer. I will tell you that because we're not in class, you're watching this video. I will tell you that the two numbers, the n value and the n minus 1, n minus 3 value, we're going to take those two numbers and we're going to multiply them together, which is still not enough to finish the formula. We still need to do something else, but I want to tell you, it is a multiplication problem. So 3 times 0 is 0. That one does work. But 4 times 1 is not 2. 5 times 2 is not 5. And 6 times 3 is not 9. And 7 times 4 obviously is not 14. So there still is something else that needs to be done to the formula to be able to complete the rule. When you believe you have the rule that works, then I'd like you to use that rule to figure out how many diagonals there would be for a decagon and for a dodecagon, and turn the video back on when you're ready to continue. So the first answer is 3 times 0, and we still got to do something to that to get a final answer of 0. And whatever we're doing, we have to come up with a rule that works for all of them. So 4 times 1 definitely isn't 2. So we got to do something to that answer to get to the final answer of 2. Same thing here. 5 times 2 is not 5. And 6 times 3 is not 9. And 7 times 4 is not 14. So hopefully you determined, and it's not so much in the first one because 3 times 0 is 0, but hopefully you determined that to get to a 14, you got to take the 7 times 4, which is 28, and divide it by 2. That gets you 14. 6 times 9 divided by 2 is 9. 5 times 2, which is 10, divided by 2 is 8. 4 times 1, which is 4, divided by 2 is 2. So all these answers are being divided by 2. So if I want to find the number of diagonals for a 10 guide, I have to go to the top of the page and draw them all in. Take the number of sides, which is 10, times the number of diagonals, which is 10 minus 3, all divided by 2. So we're going to take 10 times 7, divided by 2. So hopefully you found that for a 10-gon or a decagon, there are 35 diagonals altogether. For a dodecagon, there's 12 sides, or 12 vertices. There's 9 diagonals coming off of each vertex. And that's twice as many. The reason we're dividing by 2 is because when I draw in a diagonal, it's going to 2 vertices, not just 1. So I'm dividing by 2 because 12 times 9, as well as 10 times 7, is twice as many diagonals as actually are drawn. So you have 9 times 12, which is 108. 108 divided by 2. So a dodecagon has 54 diagonals. So again, if I go back up here to the top, kind of talking about the idea of too many, if I would look at the picture here, hopefully it would take much to convince you that there's 2 diagonals coming off each vertex, and there are 5 vertices. So 5 times 2 seems like that would be the reasonable answer. You have 2 plus 2 plus 2 plus 2 plus 2 plus 2, which is 10. But the answer actually is 5 because this diagonal here is getting counted twice. One's up here at A and one's down here at B. And so that's the reason why we have to divide by 2. Same thing with the heptagon. There are 4 diagonals coming off each vertex. So it would seem reasonable to say, well, the answer is 7 times 4, there's 28 diagonals. But again, each diagonal is getting counted twice. So we have to divide by 2 to get that final answer. There is an additional activity in this content block on lesson 2-3, diagonals, which is a decimals activity. There are 5 problems. So, so go ahead and go back to the content block and click on the decimals activity, complete the 5 problems. I did add in a couple of videos just to make sure that you see the problems being done if you're not getting the correct answer. When you're finished with that, then move on to your homework assignment. Please don't begin the homework until you've done the diagonal activity first, because there are a couple of problems in the homework assignment that comes from today's diagonal activity.